Good morning, my dear students. Today we're going to explain Chapter 1, Nervous Communication, Documents 2, Nervous Information, Nature and Propagation, Part 1. By the end of this video, the students should be able to cope with the following objectives. Recognize the instruments used to highlight the potential difference in a nerve cell. Define the resting potential. Explain the existence of the resting potential. Define the action potential. And finally, identify the different parts of the action potential. Frankly speaking, we all know that the neuron is a nerve cell that is primarily used in the transmission of nerve impulses or nerve messages for long distances. And now, here comes up the first question in this document. How is the condition of this nerve cell at rest? In order to answer the question, we must determine the state of the neuron at rest. I mean, in the absence of any stimulation by using an experimental device. Knowing that the axon or nerve fiber is an extension of the neuron cytoplasm, such axon is taken from a squid, a marine animal, which is large enough to demonstrate easier and more solid experimental results. Now, it is extremely vital to recognize the experimental device and its components that are used to determine the state of the neuron at rest. This is the physiological liquid where the axon is inserted. Here, this is the nerve fiber of the squid. This is the measuring device. And this is the receptor electrode. And finally, this is the reference electrode. Basically, in order to record the resting potential, a galvanometer or voltmeter is used or an oscilloscope is used. This video clearly shows that the needle of the galvanometer reads 0 millivolt when the two electrodes are connected to the surface of the nerve fiber and displays a series of straight line signals on the screen of the recording device, indicating that there are no potential differences between the two electrodes at rest. But if we insert the right electrode inside the nerve fiber, the needle deflects to minus 70 millivolt, indicating a resting membrane potential difference between the negatively charged inside and the positively charged outer side of the membrane nerve fiber. Now, after this experimental application, one can absolutely define the resting potential or resting membrane potential as the potential difference between the negatively charged interior of the membrane and the positively charged exterior. This is really known as the membrane potential or resting potential. At this moment, two logical questions pop up. The first one, why is the interior negatively charged? And the second one, what is the origin of the resting potential? And to answer these questions, we must follow the upcoming explanatory video that helps us to explain what we are looking for in reality.
The human brain alone contains about 100 billion nerve cells, called neurons. A neuron, like every other cell, has positively and negatively charged ions inside and outside. Further, a resting neuron has a greater negative charge on the inside surface of the plasma membrane and a greater positive charge on the outside surface. This partitioning of charge creates a voltage difference across the membrane known as the resting membrane potential, which can be measured using a voltmeter. On average, an intracellular electrode records a value of minus 70 millivolts. The resting membrane potential depends on two factors. First, it depends on the presence of sodium and potassium gradients across the plasma membrane. Specifically, there are more sodium ions outside the neuron than inside, and more potassium ions inside the neuron than outside. Second, the resting membrane potential depends on the differential permeability of the plasma membrane to sodium and potassium ions. Leak channels in the plasma membrane allow sodium and potassium ions to diffuse or leak down their concentration gradients. The membrane contains many more potassium leak channels than sodium leak channels. Thus, the membrane is much more permeable, or leaky, to potassium ions. As positively charged potassium ions leak out of the neuron, the inside surface of the membrane becomes negatively charged compared to the outside surface. If potassium was the only ion moving, the potential would stabilize at -90 millivolts. However, positively charged sodium ions leak into the neuron, which slightly offsets the negative charge and raises the voltmeter reading to -70 millivolts. Sodium-potassium pumps actively transport sodium ions out of the neuron and potassium ions back in, compensating for the sodium and potassium leaks. Thus, the pumps help to maintain the resting membrane potential.
Frankly speaking, the resting membrane potential depends on two criteria. First, the uneven distribution of ions on either side of the membrane, where the intracellular medium is richer in potassium ions, while the extracellular medium is richer in sodium ions than the inside. The second point is the selective permeability of the membrane to ions from the leaking channels or leaky channels, where they encounter or display a greater permeability for potassium ion as compared to sodium ions. Thanks for watching, and I hope you followed the explanatory information interestingly.